Welcome to part 2 of our discussion on waveforms and signals. This lesson focuses on dynamic waveforms. In addition to static waveforms, we also have dynamic waveforms. And dynamic is indicating that this waveform is changing with respect to time. And we can also have dynamic and aperiodic, as well as dynamic and periodic waveforms. An aperiodic is going to indicate that there are no repetitions in y of t for an analog signal or y of n for a discrete or digital signal. So one signal that is both dynamic and aperiodic is the step signal. The step signal has an abrupt change at time t0, where it changes from an amplitude of 0 to an amplitude of a0, and this is occurring instantaneously at that time t0. As an example, if you stand in a dark room and then you flip the switch to turn on the lights, well, that's a step waveform. The lights go from off, 0, up to some amplitude of light, let's call it a0. To write this mathematically, we'll write y of t equals a0 times u, where we're using u to denote the step waveform, u of t minus t0. And this indicates then that the step is occurring at time t0. I can describe u of t by the following. For a step waveform or a step function, u of t will be equal to 0 for t less than 0, and u of t will be equal to 1 for t greater than or equal to 0. Therefore, if I include this t0 in my equation for y of t, I can indicate that my step function is occurring at some other time than t equals 0. In this case, it'll be occurring at the time t0. Another dynamic and aperiodic waveform that I'll encounter in my mechatronic systems is the pulse waveform. Now this pulse waveform will go up to an amplitude of a0 at some time t0, and it'll fall back to 0 at some later time t1. I can write this then as the difference between two step functions. Here, y of t will be equal to a0 times the quantity u of t minus t0 minus u of t minus t1, where in both cases u is defined as the step function from the preceding slide. And there's a host of other dynamic and aperiodic waveforms. You'll often encounter the impulse and the ramp waveforms in your mechatronic systems as well. The impulse being where all of my energy is applied in an infinitesimally small amount of time, and a ramp function is something like if I'm using a motor to track the sun, let's say, right? I'll be following an input and that'll be ramping up with respect to time. Now we also have dynamic and periodic waveforms. Periodic indicates that the waveform repeats itself with respect to time. So y of t will be described as y of t plus capital T, where t is the period of the waveform. A standard example of a dynamic and periodic waveform is the simple sinusoid, which has just one frequency component. Given a frequency of the sinusoidal signal, omega, we can calculate the period of the sinusoidal signal as capital T equals 2 times pi over omega. We also have a phase of the sinusoid phi, and the time at which my signal crosses this 0 axis, let's say, will be t of phi equals minus phi over omega. For this signal, I also have a DC offset, A0. And we'll talk more about DC offsets shortly, but I'm effectively shifted the entire sinusoidal signal off of the 0 axis. And I have an amplitude of my sinusoidal signal, capital C. So this sinusoid goes from A0 minus C up to A0 plus C. So we can write this sinusoidal signal as y of t equals A0 plus C times sine of quantity omega t plus phi. Thus, this is a dynamic and periodic waveform. This signal is both changing with respect to time and repeating itself. Complex periodic waveforms contain more than one frequency. Here we have an example of a complex periodic waveform. If I were to zoom out a bit, instead of 0 to 10 seconds, maybe 0 to 50, you'd see this complex signal and you'd see the period and be repeating itself. And these complex periodic waveforms, they're really ubiquitous in mechatronic systems, particularly when you have signals that you're sending, and if noise is coupled in, you'll see the complexity increase rather quickly. In this case, the signal that we see on the screen will be composed of sinusoids of varying frequencies, right? Different frequencies all compiled together into one complex waveform. Let's take a look then at how I created this complex waveform. I start with a simple single frequency sinusoid, right? So this would be dynamic and periodic waveform. And in this case, y is equal to 5 times sine of t. So my frequency omega is 1 radian per second, and my amplitude a naught will be 5. And then there's no DC offset to this signal. So if you look at the amplitude of signal amplitude of 0 volts, you'll see the symmetry of my waveform about that 0 volt line. I then continue by creating a second sinusoidal signal. In this case, I have an amplitude of 3, a naught equals 3, and I have a frequency omega equal to 2.5 radians per second. So I get my blue curve here. And once again, we see there's no DC offset, so it's still symmetric about the 0 volts line. However, the amplitude and the frequency of this blue signal has now changed. It's different than the original red signal. When I add both of these signals together, so at every moment in time, add the blue curve and the red curve together, I'll end up with this complex periodic waveform here in black. So this waveform is described as 5 times sine of t, that's the red signal, plus 3 times sine of 2.5t, the blue signal. So every moment in time, I add up the red and blue signals, and I plot them as the black signal here. And so the signals that you experience with your real mechatronic systems, they're going to tend to look much more like the complex waveform here than the simple sinusoids. So you have to appreciate that in this complexity is buried a number of sinusoids, all at different frequencies, and they're all adding up to give you this complex periodic waveform.